Hi, everybody. After lunch, this is the most difficult presentation and session of the day because in about 10 minutes, lunch is going to kick in, and as hard as you try, you'll do what we call a light check. So I'll try to keep you entertained.
Call that the church nods.
Yeah, sure. So, as it says here, I'm Peter Murray, and I'm from Virtual Instruments, and I got a big long title here for the presentation. Virtual Instruments, some of you probably know us a little bit better as Swift Tester, Load Dynamics, or that Swift box. That's what I come from. And we've, for about about 10 years now, we've been building and enhancing on what I still will say is the best load generator on the planet. Okay, I know I'm doing a little bit of commercial stuff. I should shut up and stop doing that and just talk about what I'm talking about. But I want to give you a little background. So I've been an SE from the time we started out with this. And I say that I have the best job in the world for a 7-year-old boy. I break stuff and people give me money. And I don't even have to fix it. That's my job. And it's pretty cool. And what we have, actually, we can break almost anything pretty easily. Okay, enough. The reason I tee it up that way is that I just want to talk to you about testing. So I guess about 4 years ago, I joined something, the SNIA Solid State Storage System Technical Working Group. We call it S4 Twig because hardly anybody can remember the full name of it. And the goal of it was to come up with a methodology for testing. Originally, we said we want to test solid state arrays. Well, turns out if you get the right methodology, it doesn't matter what you're testing. If it's storage and you test it that way, it won't penalize anything particularly, and it'll help people show off their features to their best effect when you're really testing. And over the years of doing this, I remember the first time we came here and people said, Swift what? And no, we'll talk to you later. Oh, that looks like a kind of nice little wrapper around SMB torture. And a lot of things were said back then. And over the years, we've gotten more and more people to know us. More and more people are using us. It's pretty much all of the vendors, certainly the tier 1 vendors, most of the second tier, and now a lot of enterprises. And the reason that they use us is that we help them test their equipment the way it's going to be used. So we're saying test storage arrays the way they'll be used, and this is the first of 2 presentations. So I'm talking to you guys as storage vendors, or probably most of us here. Is that clear? Any service providers or any standards trolls like me? Or okay.
There's at least one end user here.
Really? Oh, I'm sorry. That's right. We'll convert you too. Okay. So I want to talk to just give you some ideas of how we do what we're doing. Now, there is this Solid State Storage System Technical Working Group, I got it out again, that's working on coming up with a methodology for testing flash arrays. There's still a lot of discussion. There's still a lot of viewpoints. So I'm going to give you the perspective that I have from my company. And it's not just from me. We have a professional services group that goes out and is doing proof of concepts and helping people do testings and doing bake-off and things like that every week. They're out doing something new. And this that I'm going through is kind of a distillation of what we've been doing for a lot of years. I hope you find it useful. So I'm going to talk blah, blah, blah. I'll talk about these things. If I miss anything, come back and yell at me later. And as I said, this is where I'm going to talk about the methodology, the way we believe things should be done. Wednesday afternoon, I'm going to do a second presentation about the way that we have implemented our methodology and what we do and how it works. So, solid state arrays became mainstream when nobody was looking. Yeah, there's still the hyperscalers are using drives and more power to them. They've got a working model and it goes great for them. But in enterprises, solid state storage is displacing the old disk drives. Spinning rust is in use less and less. There's some things that are different about them. We really need to test differently. In the past, we had programs like Iometer and Theo and others that did straight I/O testing. They were developed from disk utilities. They were not concerned with anything other than trying to get access and get something back from a drive. And you could test randomly across a drive, or you could test sequentially, and you could do reading and writing together. Well, with solid state, the world kind of changed. We've got new features, and we really need to test for those features. Anybody ever used to see dedupe and compression on a spinning drive? Well, you could wait a really long time to get your data back and do it, but nobody bothered because it didn't help. Well, that's changed a lot. So we're going to look at some things like that. And we believe that the best way to test now isn't just to use these synthetic read-write 80-20 mixture of synthetic writes and reads and random or sequential and all that, because it doesn't tell you how applications are going to run in a data center. What's going to give you a better idea of what's going to run in a data center is to emulate an application as closely as you can. Now, that doesn't mean that we're perfect. We still got a long way to go. It's a process we're going through. We're working like crazy on it right now to get finer and finer grained control of what those applications look like. So I want to talk now about the elements. So what's common about an application stream? It has locality. That means there is a certain pattern to where things are written and when they're written, where they're read and when they're read. And this is true even though people talk about the application blender effect, saying that especially when you're working with a lot of VMs, everything looks random. I'm going to show you a chart, actually an HTML page, that says that's not true. And that what I'm going to show you is what we found is more honestly what's out in the world. So we need to understand locality. Where's stuff being written? Why, how is it being grouped to write there? Access patterns. Anybody, if you go in and look at performance stats on an array, especially older arrays, you'll look at it and say average block size 33K. Well, I still haven't seen a 33K block in my life. But it's a mixture. So they take all of that and crunch a number, and 33 is what they give you. Well, it's made up actually of multiple different sizes. So we want to test with those sizes. We want to test in realistic ways. Uniform random write. I'm going to hit this again, and so I'll be repeating myself. But uniform random write is the way some vendors say to test solid state arrays because it makes their array look really good. Vendors will say test with this certain IOP pattern using this particular load generator, but they don't use bursts, and it distorts the performance. They'll say test without data content. Who needs that? Well, it depends. Not every array is good for every single application. If you've got a highly compressible application, then you probably want to test with compression and dedupe to find out how well it does, because that's going to lower the cost of what the array that you get. And lastly, testing with bursts. Sub-second bursts are present everywhere. Anybody ever seen a computer that sends traffic out at 100 IOPS? No, it dumps the file. It gets rid of it. So we're going to talk more about that. So we want to understand what's going to happen in production. This is from my marketing guy. So for those of you who hadn't figured it out yet, you don't get as many write cycles from solid state storage, okay? Okay, we get it. So they try, a friend of mine at one of the vendors says it's best to call these things write avoidance arrays. So they coalesce a bunch of writes up into a memory page, and then they lay them down. And then they watch that, because where that information was coming from when it was laid down is likely to be followed by other stuff in that same region. It's the way an application operates. If you think of adding to a customer file, it's pretty sequential. You're adding all day long. So in many ways, those bands show up and you see them. So the write time really is implementation dependent. If you're running JBOD, there's not so much. But if you're looking at most of the modern arrays now, they are doing a lot of sophisticated computing and math to write things as efficiently as possible, to avoid overwrites, to speed access when somebody does read it back, if they ever do. And we want to make sure that gets done right. Oh, I said here, reading is free. Well, reading doesn't pit the solid state, the solid state memory. It doesn't cause any problems. Writing does. So it's a little bit different, but reading still introduces problems with, you can get blocked. If an array is trying to get to some location and it's being written to at that moment, they either have to go to RAID and get to another copy of it, or they have to do some sort of work to get to that to keep it going as fast as it needs to be to maintain the overall latency. We may, well, in fact, in most cases, I won't say in most cases, in many cases, data reduction, which is compression and dedupe and pattern reduction, requires that post-processing occurs. It's just not enough time. And it's going to be interesting to see what happens with NVMe, because at the much higher data rates, we're going to have something that can just scream it, slamming things down and making less space out of it. And that may be pushed to the side. That may all be post-processing, as we see. That's still unfolding. So I say it typically doesn't affect write speed, because they'll just go through initially when they're taking things in and do what they can to that data and save the rest for later when they can come back and look through the array. Okay, preconditioning is a religious topic. That's for my friend in the back. We have, there's a lot of different opinions out that, everything from, oh, you overwrite it twice with random data, you go back and splatter the data for 20 seconds and then you're done and you've done your preconditioning and it's not going to change very much. There's other people that say you need to do this for days. And the reason that you're doing that is we're not writing to disk drives anymore, we're writing to metadata. We're writing, when we do a write, the array looks at that block that comes in. First it sees if it's a duplicate of something that's come before. If it's not, great. Then it looks at it and sees if it can smash it to make it smaller. And if it can, it writes. If it can't, it writes. And that's how the writing occurs. And if that same pattern is seen later, you don't have to write. You just make a reference to it. And the smaller the chunk you use, it goes down to about 512 bytes is the smallest I've seen so far. If you go down to that smaller chunk, then it's more likely that you'll see duplicates. It's just, no, statistics say that that's the case. So there's a whole bunch of trade-offs that vendors use for this. But this can affect the speed of writing, can affect, preconditioning can affect all of this. And I say more Wednesday, come hear me Wednesday. Question?
So what other forms of preconditioning are there, such as simulated fragmentation, or what else might be?
The latest argument.
Really?
Yeah, I don't want to spend a whole lot of time on Tate. I'll spend more, I think, on when I talk on Wednesday. But the latest argument is either you do this for a long time, you try to do it across block boundaries and do everything you can to dirty it up and mess it up. But all you're really trying to do is to come up with a bunch of checksums. And then look for those checksums. And if they exist, you don't store again. Some vendors can do dedupe across block boundaries as well. So something gets appended and data moves out, they can still go find that new chunk and just save a reference to that. It depends on the vendor, and the algorithms are getting more sophisticated all the time. Okay, so we were trying to emulate real applications. Duh, that's what I already said. Avoid uniform random write distribution, because that's a particular vendor tactic for selling arrays. And it works very well if you have a lot of reserve flash. Now, all the vendors have some reserve flash. What's presented to you is less than what's there. And the more that you have in reserve, the less you have to worry about what's happening in the background. And that really matters most for garbage collection. When an array has to stop to get and blank a particular memory page, it's not going to be a block anymore, it'll be that memory page. It takes time, and searching for that can be very painful. And vendors that use less reserve flash have a harder time getting to do that, and the array will reflect that by slowing down, especially if you're doing uniform random write. Can anybody tell me an application that uniformly randomly writes and never reads?
Logging.
Pardon?
Any logging process like Exchange, web servers,
Well, you're never going to go look at it.
you got it.
You're never going to go look at it. Well, okay, and if you're going to say exchange and servers, I'll make an argument back there. You're not seeing it at the rates that are going to choke a solid state array. But point taken.
Okay.
Okay, it's unlikely.
It's
also not random, right? It's going to be.
That's right.
They are sequential.
Yeah, there's sequentiality to it. So it's doing that random that comes from FIO and comes from iometer was it was relevant when we're doing disk drives. It's just less relevant now. And that's not what your typical application looks like. And just wait till I get to that slide and show you. And I'm going to be so happy that if it doesn't work, I'm going to be really irritated and I'll have to take you all outside or something. Okay, so.
We'll ask for our money back.
Yeah, I know. Well, and you're getting what you pay for today, I'll tell you. So don't do uniform random writes. Use multiple block sizes, duh. Now, some people will argue back and say, oh, my Oracle application is every time 8K writes, that's all it does, and that's the end of the story. Well, sometimes. But one thing about flash arrays, what are people doing? They're combining applications. They're not running just one application on a stand with multiple racks anymore. They're combining these together, and when you get that changes it. More on that later. So we also want to make sure we test in the presence of the other stuff that goes. All the enterprise features, backups, snapshots, replication, periodic access like end-of-month processing and quarter processing, whatever that might be, which has vastly different traffic patterns. Okay, so what do we care about? Write-read ratios, random sequential access ratios, the access pattern drift. This is, what am I losing it here for? This is where we talk about clustering, where we talk about, oh, never mind, I'll come back to it later. Block sizes, alternate paths. When you're writing to an array, especially if you're using fiber channel with MPIO, you've got stuff coming in multiple paths coming into the array. So you want to test in a way that looks more like that rather than just trying to get one endpoint and read everything that came in there, because you may only be getting half of the story. There may be traffic coming in from multiple interfaces. Okay, so locality is this idea that stuff tends to get clustered when it's written during a day. And this is even true with blended applications. The I/O blender effect that has famously been talked about with virtualized applications isn't entirely true. There's still some locality to this. So we're defining when something is written or read, that's spatial locality. Or where is something is written or read is spatial locality. When it's written or read is temporal locality. Both of those are present. And hotspots represent this locality. The hotspots, you tend to be writing in a narrow area, and that tends to drift over time as you're writing, okay? So if you don't test with locality, you're not stressing the arrays they're going to be used, the way they're going to be used in production. And again, if it's just JBOD, that's going to have less effect than if you've got a controller with sophisticated algorithms that are deciding what to lay down and when and how and all that. With a lot of arrays today, you don't write to LUN 0 offset 100. You write to a logical representation of that, and where that gets put on the array may be anywhere. That's because of wear leveling. The whole idea is to make that array last as long as it can, so you don't want to keep writing to the same location and burn it out. So wear leveling takes care of that. So all of that is abstracted when you're writing to the array. You're writing to a logical space, it's writing to the physical space out back. So I've got a demonstration. So it's showing write locality for a LUN with real life Oracle ASM access. Horizontal access is going to be the LUN broken up into 100 parts. So if something comes in at the left, that's towards the lower end of the address range. If it comes in at the right, it's towards the higher end of the address range. And each refresh of what I'm about to show you comes for 1 minute interval. This is not, you're not going to be able to get this, unfortunately. I wasn't able to figure a way to save it, but if you come to me, we can somehow get you, I'll send you the location or something, because it is pretty interesting to see this. So the height is just normalized for each refresh. It's not trying to show relative intensity, rather to show that the hotspots are there and that they move over time. So My friend Lou Leidickson at Pure Storage is the guy who got this for me, and now is the moment of truth, and we'll see if my access to the Hyatt network worked. Click. Okay, so now I'm going to have to come up here and dance and show you what. There it is. There it is. No dancing. And you're not seeing it. Let me see if I can do this. Yeah, I'll just let it run for a little while. This is why you go and try everything before you do an actual presentation. But you can see what's going on there. This is not random. There is a definite pattern to where everything is being written, and this pattern changes over time. Sometimes there's a lot of clustering, sometimes there's less, but this is one of many views that Lou has done, and they all reflect this. They have not been able to find applications that don't do this. So, yes, sir.
Scroll it down.
Yeah, sure. There. So it's just, it's a representation of 1,000, the LUN broken up into 1,000 different sections, okay? And it gives us a little bit more to see down here. So this is happening. This is happening all the time. We just hadn't been able to see this yet. One thing that I don't want to sound like a commercial for these guys, but they've got a way of taking a standby controller and just monitoring everything that's coming in. And they were able, from that, to generate these graphs that show that locality as traffic is coming in. Pretty cool stuff. So, it's there. Ha! I proved it. If you believe it.
That's the virtual view or the hardware view?
That's one LUN. And actually, yes, it is the virtual view. LBA. No, because the way it goes on the back end is who knows. That's all done for. The algorithms take care of that for their wear leveling. It worked. I'm all pleased. Okay. There. Okay, good. I'm back on it. Okay, we just talked about this. Access is not uniformly random. Hotspots are accessed more frequently than others during a defined time period, and it varies according to what you're doing. We have some examples here like index temp files, logs, journals, things like that. And we want to, when we're testing, emulate that there are hotspots and emulate that drift as well. Here's one example that we saw of where things were written. So 1% of all access regions got 35% of the IOs. That's quite a bit. And it varies according to each of those, and you get up to the higher numbers get less of the IOs over time. And the FIO developer, as it says here, says that this is a simplified example, and that it's actually even a little bit more complex than this. But they're present, and skew is present. So, yeah, 25 to 35K is the average reported block size. We look at vendor performance reports, vendor performance processes. Virtually every vendor can produce a CSV file that talks about performance during a time period. For any of you guys who work for vendors that are willing to share with us, we beg you, please do, because we can take the output of that CSV file and turn that into input for a workload model. I'll talk a lot more about this on Wednesday. But the idea is that we take this information that's reported from the array. Did Eden live? Eden left. Darn it. Eden Kim's working on another model that works by using a small program in an initiator or target, if I understand it right. Is that correct? That is able to record what happens on the way out or going through one of the interfaces. And he gets pretty good resolution out of it. The problem that we have really is getting adequate resolution for this. If you get a 5-second interval, you could have a horrible spike for a couple of seconds that really impacted performance, but you average it over 5 minutes and it looks like nothing. So the better we can get this, the better. And without being too much of a plug, Virtual Instruments is working on that. Now, the guys, the VMAX team, is got something called Trace SRT that allows them to get really fine time-grained intervals. The command, what it was, how long it lasted, and things like that that allow you to recreate a really accurate model of what happened during that time. And that varies all over the map, from some vendors that give you these 5-minute reporting intervals, which is not very useful at all. It's still maybe a little bit better than doing things completely the old way of testing, but the finer the grain time interval, the better, and we're working towards getting below 1 second. It's a limitation where we are today of computing. Trying to move all that data in at the same time, say, oh, by the way, we did all this stuff, is pretty difficult to do. But we're going in that direction. So 25, 35K, often applications don't use uniform block size across an entire application. We want representative block sizes, so you set up percentages of different block sizes and you mix those in. Now, we are doing a statistical model. This is not an exact replay of an application, because if we had the desire to do that, we'd have to have a second data center to collect all the data to do it. Because, a PCAP at 10 gig, much less 40 gig or 100 gig, just huge amounts of data. So we summarize, distill that down, and we're using that. But we do a synthetic model of it. So burst, here we go. Craig is in the back of the room to correct me if I blow this one again. So here's this burst that happened during a particular time period. The host performance, they see this going up. During this time, the IOPS didn't change. Latency didn't really change. But there was this huge burst that happened. Okay? So it comes and it goes. These are real. Computers don't send 100 IOP files, right? They get rid of them as quickly as they can. When that happens, it tends to load up the CPU, it loads up the queues, it can mess up especially in the processor memory, the buffers, and the queues, and can dramatically lower performance. There's a certain vendor that's saying recently that we should all increase our queue depths. And we argue just the opposite, that the lower the queue depth setting, the more likely you are to avoid network congestion, and you're going to get more work done during a given time. So yeah, 50 milliseconds. Okay, yeah. Is this here? No, it's not. Those heavy burst times are actively impacting performance while they occur. The more things are sitting waiting to get done, the more it affects everybody going to that array. So for reads or writes, which one is it? Okay. So we see here that we have minimum pending exchanges. There was a lot of times where there was just nothing happening on here. Over this period of time, it's almost an hour. We'll see the top average pending. There was actually, during a whole lot of the time, a lot that actually was waiting to get done, which means somebody's getting backed up. And we see the max pending up here average about 40 and lowest about 20. That was happening over that time. Max, we see that it was well over 100. So this is what's happening on the wire. And this is going to be what really can hurt an application. So let's look at reads. If this was just a constant number of IOPS, we're getting, 40 to 80K IOPS. We would see a much more even response time. What we're seeing here is a range of 200 to 400 over a 50 millisecond barrier. So the bursts were 40 times as high as the average. What this means is that even in a second, stuff hits the array, it gets backed up a little bit, and then it drains and keeps on going. And there's periods where nothing else is going on, but where those peak times occur, it's actually seriously impacting the performance of that array. And that gets missed a lot. IOPS, we're seeing it's only about 2K IOPS here, but there was significant amounts of delay there. Okay, so writes, real writes. Here's an example. We're looking at IOPS. IOPS were almost nothing there except for one big peak during a brief time. But when we look at the 50 millisecond peak, we see that it's even worse than we saw when we were looking for writes than for reads. So here's the reads. Oh, no. There's the reads, the writes. And those bursts were slowing us down. Okay, so there's a range of these as well. And that's what this is showing. The peak, the bottom, the mean. So a couple of these guys were really were working getting greatly increased latency. It was less bad over time. But the IOPS here were much more stable. And you're going to see that in a real application. Sir, ma'am.
So where is this being observed at?
This is being observed off of a wire using a tap, using virtual instruments, virtual wisdom application.
So this is our data center.
Yeah.
This was observed in. That first image that we showed you was an actual customer image issue, where the only observable problem in their environment where the latency more than doubled was the fact that they were having these microbursts.
Yeah. It's the only thing that changed.
We also went through and analyzed our customer data, and this is common in all of the data that I've had access to. That, most of the time, every second, there's a time period within the second where the report is being done. And in some cases, the writes, all of the writes for the entire second occur within microseconds. So it gives you an idea that if things are not a flat line, when you look at subs or second, they're all over the map. Even if you've got a state IOPS, what's happening in some points that is very first, lots of spikes and out.
Right. And we've had multiple vendors come back to us and say, you suck. You give lower performance than Iometer does, or VD Bench, because they were running VD Bench without bursts. And yeah, we do. When you make the traffic more real, you don't get as much data through. So, writes, reads, writes, the range of response times. Now, load dynamics, our load generator, by default, breaks up transmissions and bursts them in less than a second. That's the way that the product was designed and the way that it works. So you'll see here we have a second broken up into 10 pieces, and that those bursts are taken. And when we ran tests against arrays, performance was slightly lower than what they would get running something like VD Bench without any bursting. And this is what those arrays are going to see in production, not that steady flat line that you get out of a storage test tool. So we're seeing here we're getting about what am I trying to read here? Oh, actions, 25K IOPS here, and we're getting a response time of about 40K microseconds. 40 milliseconds, sorry. 40 milliseconds. That's with the bursts. 40 milliseconds pretty bad. Now, if you take this down to 80%, take that rate before and drop it down by 20%, we see that we actually were getting 20K IOPS through. We're getting down to 6 milliseconds response time. This is all what we're talking about, sizing the array for what it's going to really see in production. Okay, so that's running at 80% of maximum. running without bursts, which is what a lot of guys report as their numbers. They'll take and just run this straight and meter it out. And we see that we're showing 15,000 or 25,000 instead of the 20,000 that we saw at the last screen. But they're showing it at 1.2 milliseconds latency. And this is what they publish. If you're sitting in the data center running applications, this is not what those arrays are going to see. So these are the hero numbers. And testing with those bursts, testing with that realism is going to give you a lot better idea of what you're going to get when you really run the array. So here's the difference here. I love this one. So with bursts, we saw they were getting 20K IOPS, throughput of about 1250 megabytes, 6.5 milliseconds latency, and this is the real world. With bursts, 25K IOPS jumped the throughput up slightly, but hugely increased the latency. Unacceptable. And without the bursts, we're seeing 25K, just like we were seeing with bursts, but we're seeing 1.2 millisecond response time, which is a myth, but which is oftentimes published. So bursts matter. Okay, on. Any questions about that before I go on? Okay, data content. Most of the arrays are using data reduction, deduplication, compression, and pattern reduction. And like I said, if they see a block of all zeros, make a reference. Don't store anything. It's a metadata reference. If it is, if something comes in, they checksum it. If they haven't seen it before, they try to reduce it. If it gets bigger or it doesn't reduce, they save it as is. If it does reduce, they save it down. And then they'll have a varying number according to the array of times they can repeat that before they have to make another save of that same piece of data. Coming back out the other way, because we have solid state memory now and we have faster processors, it's possible to what they call rehydrate or re-expand that data and get it out to the sender much more quickly. So all of those are there. Not all arrays do compression, not all of them do dedupe, not all of them do pattern reduction. So you want to know what's going to work, test for it. And it's not just to say, oh, we got this dedupe ratio or this compression ratio. This can save a customer a lot of money. If the more efficiently data can be deduplicated and compressed, especially at higher rates, the less you need of that stuff. And for customers, that's an important consideration. Okay, we all want to sell more as vendors, but we also want to be considerate of this as well. So we create data content patterns. We turn those into streams, which are essentially take blocks in repeating in various amounts. You'll have a block with a certain checksum may be repeated 10,000 times during a test. A different one may be repeated not at all. It may just be random. But those combination of them give a stream that looks like an application. I talked about the repeating and non-repeating patterns. Pattern lengths vary. As I said, some arrays can detect patterns across block boundaries, so they're able nominally to get a little bit more compression out. Next is thread count and queue depth. So when you're testing, not only do you want to do the best testing, we'll say, okay, I want to understand a technology. Okay, I choose that technology, and then I want to know what configuration of that technology is going to work best. And when I'm doing that testing, I want to be able to test using different queue depths to find out what gives me the best performance, and combining that with different thread counts to find out what the capacity, max number of users and such is going to work for a given size of an array. Maybe I have to go up to a second controller, or I have to do a scale out to go to multiple nodes to essentially maintain the latency that I want for that application over time. So we find the max IOPS an array can do per thread, per queue depth, and then a total for a given number of threads and queue depth. And then we increase this to find out where the limits are. You shouldn't really be testing for today. You want to test what an application can do today, and then the lease period is going to be somewhere between 3 and 7 years, something in there, and they're going to have to refresh at the end of that time. So you want to make sure at the end of that time the array is still performing. This is important, even going back into testing with disk-based arrays. There's a company we worked with that had installed, they had 5 stands, and they put the first one out when their traffic was relatively low, worked fine. Second one came in, third one came in, fourth one came in, and the whole thing fell apart. It was a limitation that they didn't understand in that particular array, and it caused a very public outage. So oops. So that's why you want to test up to what your expected maximums are going to be. Next, because we're talking about solid state, in many cases, not all, I'm not trying to claim that everybody's going to be throwing 50 different applications on one array, but we're seeing more of it coming, right? We're seeing more of that happening. So we want to test those applications together, find out the performance of an individual app, and then start combining them. And again, crank up the numbers to find out what the maximum performance is going to be. And last night I was talking to my friend SW, and he said, you want to be careful about this. I was saying, you just should test them all on the rainy day. Well, that's not going to happen if you're... the apps aren't necessarily all going to hit peak performance at the same time. So you want to be sensitive to that. Look at the patterns, you do some baselining, understand how the applications are performing, and then put them together in ways that's going to make sense over a test, say, where you emulate a day or something like that. And make sure that the additive peaks don't exceed your latency targets. You want to stay within that. So we want to emulate each application, combine them, and then test, of course, with the other processes that are going to go on, snapshots, replications, backups, periodic processing and all that. And take care to make sure that the peak times are represented, just not make this one big additive jump on top of everything. I say here, this is a work in progress. We're working on this. There's still a lot of work to be done, but to where we can do a better job of helping to represent these applications running. But this is pretty much where we are today. And we need ways of speeding this up. Somebody doesn't have usually the luxury of spending, we'll take a month to test this array and a month to test the next one. You maybe get a week or two to crank it out. And so you have to make it more efficient. We're early on in this, and it's getting better. Okay. I already said this. You want to make sure that you're sized properly, so crank up the numbers if you get an application running at a certain rate today. I think my assertion that it's okay to make the assumption that as traffic rises, the application, the components of the application are still going to work approximately the same. I may be wrong, but it's the best we know today. So try to take today's rates and boost them up and just make sure that the latency targets are met, that the system doesn't fall over on its side. So this all used to be black art. It's not so much anymore. It's not clear, but it's clearer than it was. There's no such thing as a perfect synthetic workload. The perfect workload is the workload that's running in the data center on the equipment it's running on now being moved over. But that's not a very easy thing to do, try to test 5 different arrays by running your current application on them. So synthetic is what we've got, and it works pretty darned well. Customers can see how closely their workload matches a model. We do this all the time. They'll get performance stats from their application. We will model it and run it, and we find that the peaks, valleys, the temporal stuff stays almost dead on with that. So we can emulate this now. The days of not being able to do it are gone. We can do better than we used to do. And I think this is changing where we're headed. So thanks. This is my ad. Please come hear the second presentation, which I'm going to do Wednesday, and I'm going to talk about an implementation that we've done. And I'm trying not to make this too much of a commercial. We've just been working at this for a long time, and we think we have something valid to let you know about. So Wednesday, 4:05, come on down. You can. This is going to be posted online, I think, with this latest version of the last screen that actually says virtual instruments instead of your name here. Come and see us. Any questions? Sure.
Could you touch on garbage collection in Flash devices such that, I call it the Super Bowl problem, your system is pretty idle until the one time you really have load and the counters start climbing and it may kick into garbage collection the one time you don't want it garbage.
Right, when everything gets delayed, yes. Yeah.
consistently?
There's some vendors are more vulnerable to it than others. It's a matter of sizing.
Okay.
In general, I think it's safe for me to say that the less reserve flash you have, the more prone you would be to that. And if you're operating in a JBOD environment where you don't have metadata, as I said, we're writing logically, but that turns into metadata, and what gets written physically is something completely different. There's a lot of work going on in that direction. But the thing is, NVMe is going to blow this all up. I'm looking really forward to seeing what happens, but there's going to be a lot less time to do stuff with data as it's going through, because it's going to be coming through at higher and higher rates. I'm going to use this. I was at one of those customer love-ins a couple months ago, and their comment was by 2020, we're going to be generating 5 zettabytes a day of CCTV, of video that's got to be stored somewhere. The internet's going to have a capacity of about 1.5 zettabytes. So everything to the cloud, it seems a pretty big stretch to me. Now, there's techniques that we can use to compress and do all kinds of things like that, but if it's something that the lawyer's got to see, it's still a lot. And if you're monitoring a busy time, it's going to be an issue. I just got the hook. So if you'd like to talk some more, come on, check me out afterwards. And also on Wednesday, come by if you've got the time. I'd love to talk to you a little bit more. So thanks for now.